And there's a supermassive black hole at its core. And we are delighted to be able to report to you today that we have seen what we thought was unseeable. We have seen and taken a picture of a black hole. Here it is. This is a remarkable achievement. What you're seeing here is the last photon orbit. What you are seeing is evidence of an event horizon. By laying a ruler across this black hole, we now have visual evidence for a black hole. We now know that a black hole that weighs 6.5 billion times what our sun does exists in the center of M87. And this is the strongest evidence that we have to date for the existence of black holes. And it is also consistent, the shape of this shadow, to the precision of our measurements with Einstein's predictions. The bright patch in the south that you see tells us that material moving around the black hole is moving at light speeds, which is also consistent with our simulations and predictions. And this image forges a clear link now between supermassive black holes and the engines of bright galaxies. We now know clearly that black holes drive large-scale structure in the universe from their home in these galaxies. And we now have an entirely new way of studying general relativity in black holes that we never had before. And as with all great discoveries, this is just the beginning. So imaging a black hole doesn't come easily. I can tell you that from personal experience, as can many people here in the audience. It's required long-term developments, a committed team, but it also required some very interesting cosmic coincidences. Take, for example, the maelstrom you see before you, like the hot gas swirling around the black hole. A photon has to leave from close to the event horizon, travel through the hot gas in falling to the black hole, and light rays of a millimeter wavelength, radio waves, can make that journey. Not all of them can. Then that radio wave has to propagate 60,000 years through the M87 galaxy, and then another 55 million years through intergalactic space. And then it winds up in the Earth's atmosphere, where its greatest enemy, the greatest danger, is that it will be absorbed by water vapor in our own atmosphere. So the Event Horizon Telescope uses telescopes at high dry sites so that we can see the photons that have traveled to us so far. So far, so good. We have the photons. But the M87 shadow is very, very small compared to the galaxy that surrounds it. So in order to see it, we needed to build a telescope as large as the Earth itself, given the wavelength of light we were trying to observe. And to do that, we use a technique called very long baseline interferometry, which you can see a schematic of here. Radio waves from the black hole hit radio telescopes, where they're recorded with the precision of atomic clocks that lose only 1 second every 10 million years. When you've registered these radio waves so precisely, you can then store them on hard disk drives, send them to a central facility where they can be combined precisely. It's exactly the same way that a mirror used at an optical telescope reflects light perfectly and in synchronicity to a single focus. And when we do this, we can synthesize a telescope that has the resolving power as though we had one the size of the distance between these telescopes, truly turning the Earth into a virtual telescope. All the sites that we used can be seen here. We have telescopes from Hawaii to Arizona to Mexico to Chile to the South Pole and Spain. But even this broad global network is not enough by itself to make an image. You can think of them as being silvered spots on a large global mirror. The key is that the Earth turns. During a night of observing, we are able to sweep out more baselines, more coverage of this virtual mirror to make our image. So on the left, you'll see the Earth turning. Every pair of telescopes provides us with one point on the center panel, which fills in the Earth-sized virtual lens. And on the right, you see the evolving image. The more and more data we get, the more we fill in this virtual mirror, the sharper our view of the black hole becomes, until you wind up seeing what we have as the final image there. So we've taken advantage of a cosmic opportunity. It's remarkable when you think about it. Light that left near the event horizon, traveled all the way through intergalactic space. It hit our telescopes. The Earth just happens to be the right size. So we get resolving power so that we can see the black hole in M87, whose mass and distance let us observe it. And then the Earth turns to fill in our mirror so that we can make this image. It's truly remarkable. It's almost humbling in a certain way. Now, we are 4 members of a large collaboration, and it is our distinct honor to be here to represent that collaboration. We are 200 members strong, we have 60 institutes, and we are working in over 20 countries and regions. We consider ourselves really to be explorers. Through international cooperation and innovation, we've exposed part of the universe that we thought was invisible to us before. It's our responsibility now to report these findings, and we're doing that today to the National Science Foundation, to our funding agencies, international and foundations, and to all people who support pioneering research, and also to the taxpayers. Nature has conspired to let us see something that we thought was invisible. This is a long-sought goal for us, and we find it tremendous, and we hope that you will be inspired by it too. Thank you, and now let me introduce Dan Maroney, who's literally gone to the ends of the earth to collect some of the data that we've seen here today.